Welcome back, everyone. So the last time we were dealing with the proof of the inverse function theorem. We were very sort of close to the end of the proof. We proved that, so what does an inverse function theorem state again? If you have a CR function and if at a point A, the derivative matrix of the function is an invertible matrix, then locally, that is near there's a neighborhood around A and there's a neighborhood around f of A, so that the map f from between these two open sets of Rn is a one-to-one onto map which is continuous, and the inverse which exists is continuous, and in fact the inverse is also CR. That is the statement of the inverse function theorem. We started with R equals 1. And we did prove indeed that there are such neighborhoods where the function is one-to-one onto, the inverse exists, it's continuous. The next step of the story is to show that the inverse is indeed C1. Once we do that, we will induct on R, we will use mathematical induction on R to prove the rest of the theorem. Okay, so let's proceed. So recall, so what we are trying to show here is f inverse, which is from f of u, right, to u, right. So this is open, is C1. So suppose you write this, so we were at this point, that means b plus h is f of f inverse of b plus k. Right. Now we will be tempted to use the mean value theorem, but this is a vector valued function. I mean, I didn't put the vector sign here, but it's a vector valued function, right? I'll just remove the vector sign just for notational consistency. Right. So the ith component of this is the ith component of this, which means this equals plus the gradient of the ith component at some point theta I dot k. I mean, if you wish, this is like Taylor's theorem if you prefer, or mean value theorem, whatever you prefer. This is bi, so these two cancel out. So the ith component is gradient f of theta I comma k, right? Oh, in other words, the vector h is some matrix times k, where if you take this matrix, the first row is gradient f of theta 1, the second row is gradient f of theta 2, etc. Right? So h is b times k. Now notice that as k goes to 0, theta I will go to f inverse of b, right? And that's how this theta I works, right? Almost by definition. So this is f inverse of b. Let me put it this way, the theta vector, if you wish, goes to f inverse of b. Theta I vector. Okay, this is a vector technically, despite the subscript I. Okay, for all I, this is true. All right, so how does that help? Now the point is, as h goes to 0, by continuity of f inverse, which we have already proven, b goes to the derivative of f at f inverse of b. Why is this so? Again, what is b? The first row of b is gradient f of theta 1, yeah? Now the point is, as h goes to 0, this is continuous, right? So k will go to 0. So in other words, as h goes to 0, k goes to 0. If k goes to 0, theta goes to f inverse of b, which means b will go to, notice that the derivative of f is a continuous function, right? Because f is assumed to be c1, which means each row of b goes to the gradient of the corresponding component of f evaluated at f inverse of b. In other words, b itself approaches the derivative of f evaluated at the point f inverse of b. Technically, and the assumption that f is c1. Okay, right. So b goes to this. What does this mean? This means that if you take this limit divided by norm h, what's this? This is b inverse h minus this divided by norm h. Now when I write this statement, you might immediately object saying, how do you know b is invertible? Right? That would be a fair objection. The point is, as h goes to 0, b converges to this, so this equation holds for all h small enough. Why? Because if h is small enough, this matrix is very close to this matrix, which means the determinant of this matrix, which is a continuous function as we all know, is close to the determinant of this matrix, which we know is non-zero. I invite you to please make this rigorous on your own. Yeah? Okay, so now at this point we can say that this is less than df inverse times norm h by h, because these are matrix norms. These two cancel each other out, and this goes to 0 as h goes to 0. Okay. Why does this go to 0 as h goes to 0? Again, b converges to this matrix as h goes to 0. Now if a matrix converges to one matrix, then the inverse of the matrix will converge to the inverse of the other matrix. Why is this so? The map, a matrix A going to its inverse, is a continuous map. Okay, why is it a continuous map? Because we have an explicit formula for the inverse given by Cramer's rule, right? A inverse is some matrix whose entries are polynomials in the original matrix divided by the determinant of A. And polynomials are continuous, and as long as the determinant of A is non-zero, the ratio of these two things is continuous. Okay. So what does this mean? This basically means, so what's the point of this entire exercise? What we have proven here is that if you take this, right, what do we want to prove? What we really want to prove is the following: f inverse of b plus h minus f inverse of b equals the derivative of f inverse, which is df at the point f inverse b times h plus some error term. And how must this error term behave? The error term divided by norm h must go to 0 as h goes to 0. Indeed, that's what we proved. If you take k minus this is the error term, and that divided by norm h does go to 0 as h goes to 0. So not only have we proven that f inverse is differentiable, right? So we have proven actually that f inverse is differentiable at the point b, right? So this shows that f inverse is differentiable at the point B, right? Now, B is arbitrary. The same argument applies for any B, which lies in the domain for F inverse. We have chosen the domain for F inverse so cleverly that the derivative of F is an invertible matrix throughout U, right? Remember, what was the domain for F inverse? It was this. Now, on U, the derivative of F was chosen to be an invertible matrix. That's how small we chose U to be. So, as a consequence, this argument applies for any B in that in F of U. So, this means that F inverse is differentiable on F of U, and the derivative also has a formula that simply at the point y is the derivative of f at the point f inverse of y, the inverse of this matrix. Okay. But what have we set out to prove? We wanted to prove not just that f inverse was differentiable. We wanted to prove f inverse was C1. What does that mean? Not only do the partial derivatives of f inverse exist, but they are all continuous functions. Yeah, that's not rocket science. The reason is we have an explicit formula for the partial derivatives of f inverse. We have an explicit formula for the derivative matrix of f inverse, right? So y goes to f inverse of y is already known to be continuous. We have already proven this. Yeah, and let's say x goes to df at x is continuous. Why? Because f is assumed to be C1. This is the definition of being C1 more or less. And the matrix A goes to A inverse is a continuous matrix valued function, right? And this is a composition of these three. In other words, this is continuous in y, and therefore f is C1, f inverse is C1. So we have successfully proven the inverse function theorem for the case r equals 1. Again, to state it simply, a C1 function whose derivative at a point is an invertible matrix is locally invertible, meaning that there's an open set around your point, and there's an open set in your target such that f is 1 to 1 on 2 between these open sets, and the inverse is also a C1 function. Yeah, that's what we've proven. Now our aim is to do the same thing but for CR function for any general r greater than or equal to 1. This will be done as usual by mathematical induction. Right. So for r equals 1, we are already done. Assume the induction hypothesis, right? Assume the truth of this statement for 1, 2, 3, so on until r minus 1. Yeah, where r is of course larger than or equal to 2, obviously. So we want to prove it for for r. Yeah. Now we already know the derivative of f inverse at y has a nice formula. I claim just knowing this formula and what we have done earlier is enough to prove what we want. Why is that so? Now the point is, this is CR minus 1 and hence f inverse is CR. I want to say this. Okay. So what does CR mean? What does f inverse of being CR mean? That means the rth partial derivatives of f inverse are continuous. Yeah. which would imply that all the partial derivatives up to order r exist and are continuous. Now, suppose we already know f inverse is C1, so you take one derivative of f inverse. If you prove that the derivative of f inverse is CR minus 1, what does that mean? All the partial derivatives up to order r minus 1 of the derivative are continuous. Then of course all the partial derivatives of order up to r of the function are also continuous, right? So it is enough to prove that this derivative matrix is CR minus 1. That, I claim, can be done using the induction hypothesis. Why? Because we have this formula at our disposal. Notice that y goes to f inverse of y is CR minus 1 by the induction hypothesis. Yeah? X goes to derivative at x is CR minus 1. In fact, it is CR by the hypotheses of the theorem. Yeah? A goes to A inverse is actually smooth. Right. Why is this so? Right. What is A inverse? A inverse has a nice formula, remember. A inverse by the Kramer rule is a matrix whose entries are polynomials in A, so hence that is a smooth function, divided by the determinant of A. The determinant of A is itself a polynomial in the entries of A, so that is also smooth. The ratio of two smooth functions is smooth provided the denominator is non-zero, and indeed it is not 0 in our case. Yeah? So this is a composition of three CR minus 1 functions, and we have already shown that the composition of any two CK functions is CK. So the composition of these two is CR minus 1, the composition of this composition with this is also CR minus 1. Therefore, this is CR minus 1 and we are done. Yeah. So we have proven a very deep result, the inverse function theorem. It's an extremely important result. It is foundational if you ever want to study differential geometry, partial differential equations or any such thing. Yeah, it slightly it does play a role in the mathematical foundations of optimization as well, slightly less so in machine learning, but nonetheless it's a foundational result as far as the rigorous mathematics goes, of course. Okay, so the inverse function theorem motivates a definition. Let U and V in Rn be open. A function f from U to V that is 1 to 1 onto CR and whose inverse is CR, R is between 1 and infinity, is called a CR diffeomorphism between U and V. This is fancy nomenclature. It's just a name, but it's convenient to have this name. The name CR diffeomorphism simply means that your function is CR. It's 1 to 1 on 2 and the inverse is also CR. That's all. Nothing more fancy than that. But R is between 1 and infinity. If R is 0, that is your function is continuous and its inverse is also continuous, it's called a homeomorphism. Okay. And U and V are said to be CR diffeomorphic to each other, or if R is 0, CR, they're simply called homeomorphic to each other. Okay. This is standard terminology. Okay. The inverse function theorem in this terminology can be stated very simply as, if you have a CR function whose derivative at a point, whose derivative matrix at a point is invertible, then the inverse function theorem states that f is a local CR diffeomorphism. What that means is there is a neighborhood of A and there is a neighborhood of f of A, so that f is a CR diffeomorphism between these neighborhoods, which means more simply f is 1 to 1 on 2 and the inverse is also CR. Okay. Right. Now, the inverse, so let me give you an example. This is a very famous example, right. So, suppose you take this map from 0 infinity cross 0 to pi. This is an open subset of R2 to R2 minus the set of points where x is greater than or equal to 0 and y is 0 given by r comma theta goes to x equals r cos theta and y equals r sin theta. So, I am very sure that you would have seen this before. These are called polar coordinates, right. So, you have a map r comma theta, r is positive, it is between 0 and infinity, theta is the angle, if you will, this is the picture of polar coordinates, this is r and this is theta. So, this is r cos theta and this is r sin theta, and theta ranges between 0 and 2 pi, but I am not including either 0 or 2 pi, it is an open set. So, the map r theta goes to r cos theta and r sin theta. Since I have thrown out r equals 0, I am throwing out the origin. Since I am throwing out theta equals 0 and 2 pi, I have actually thrown this, sorry, let me write it like this. I have thrown this line out entirely. Okay. So, this is r and this is r and this is theta. Okay. So, it's obviously it is 1 to 1 and on to this, right. This is easy to see, right. You can see this explicitly. If you give me x and y, you can determine r and theta uniquely from this. So, if you call this map f, f inverse exists. In this particular case, you can write a formula for x inverse, right, and conclude that f inverse is smooth. But actually, there is a much simpler way of concluding that f inverse is smooth. That is the following, that suppose you compute the derivative of f, right, at your favorite point r naught comma theta naught. So, what is the derivative? It is the derivative gradient of the first component. What is gradient? The derivative of this with respect to r, which is cos theta, the derivative of this with respect to theta, which is minus r sin theta, likewise sin theta and r cos theta. In fact, I will put a naught here. Is this invertible? Well, what is the determinant of this? This is r naught cos square theta naught plus r naught sin square theta naught, which is just r naught, which is not 0, because r is, it is demanded to be strictly positive, which means what? Which means by the inverse function theorem, f is locally a smooth diffeomorphism, which means f inverse is locally defined and it is smooth. But actually we already know f inverse exists not just locally but globally, meaning it's defined on this entire huge open set. So, by the inverse function theorem, if f inverse exists, well, it will coincide with the local inverse, right. The inverse is unique if it exists, right, and we know that the inverse is smooth locally, and therefore this f inverse is actually smooth. You do not even need to know the formula for f inverse. Inverse function theorem tells you directly it is smooth. Okay. So, this is an example of a diffeomorphism between this open set and this open set of R2. Okay. Now, this terminology raises an interesting question. We call these polar coordinates, right. We all know that these polar coordinates are useful for solving many problems. Yeah. and what kinds of problems are they useful for. For instance, in physics they are very useful if you've done any, but in general when there is any symmetry, right, when there is radial symmetry, it's convenient to use polar coordinates. Yeah. Now the point is, so we are calling these polar coordinates, which means are there other kinds of coordinates, right? What are coordinates after all, right? This is the question. What do I mean by a coordinate system? By the way, in physics they are called frames of reference. Okay. We will answer this question more precisely later on when we define manifolds, but the point is, as we will see later on, a coordinate change is simply a diffeomorphism. Okay. If you take x and y and you change it by a diffeomorphism, you get a new system of coordinates. That is what coordinates are. And I can't resist pointing this out, that Einstein's main contribution was to write the laws of physics as being invariant under diffeomorphisms, under these coordinate changes. That is what he wanted, right? Diffeomorphisms involving space and time. Whereas Newton simply wanted them to be invariant under time being fixed and space changing under linear maps. Okay. So that is the difference. Right. Anyway, that is sort of beyond the scope of this course, but yeah, so these are coordinates. This is an application of the inverse function theorem. But a most striking application of the inverse function theorem is to prove the so-called implicit function theorem, which is what we will discuss. Okay. What is the point of the inverse function theorem? One of the points of the inverse function theorem is to solve a system of nonlinear equations, right? If you want to solve this, this is n variables and n unknowns. So if you have n equations and n unknowns, you expect that there ought to be solutions, right? But that is not always the case. The inverse function theorem will tell you that if you already have a solution, right, and if you perturb this a bit, then you will continue to have solutions. That is roughly what the inverse function theorem says. Okay. So basically that if B is changed a little, there is still a solution which is near A, and in fact the solution depends on a CR manner on the right hand side. So if you change B a little bit, then there is still a solution to f of x equals the new value of B, where x depends in a CR manner on the right hand side. Okay. Roughly that is what the inverse function theorem says, right. So what we want is, if you wish, a generalization of this. Sure, on paper it can be thought of as a generalization, but in practice it follows from the inverse function theorem. So the inverse function theorem is somewhat more fundamental. Okay, so in linear algebra, so the question is, what if, like in linear algebra, we want to solve m equations with n unknowns, where the number of unknowns is larger than the number of equations. Okay, this is the question. So morally what we expect is, like in linear algebra, in some sense, if the equations are independent in some sense, are independent of each other, then we ought to have n minus m free parameters at our disposal. Okay. What does this mean? So, suppose in linear algebra you solve m linear equations with n unknowns, right. So, you solve Ax equals b, where you have m equations and x is in Rn, right. Now, if you take your matrix A and if the matrix has rank m, what is rank? Rank is the same as row rank or column rank, both of them are the same numbers, which would mean that the equations, when you look at the equations as rows, the m of these rows, all the rows are linearly independent, right. So, the equations are in some sense independent. In what precise sense? In the sense of linear independence. Then you can hope to solve Ax equals b, right. You can solve Ax equals b, but it is not just that, the space of solutions. So, if you try to solve Ax equals 0, right, then the dimension of that space is n minus m. In other words, if you have any solution to Ax equals b, you can add to it an n minus m dimensional vector space worth of vectors to get a new solution. So, you have n minus m free parameters in that very precise sense in linear algebra. So, does this sort of intuition work for non-linear equations as well? So, if you have, let us say 5 equations and 10 unknowns, would you expect to be able to solve them and have 5 free parameters, right? This is the kind of question we want to answer. Let us look at an example to see if it is a reasonable question or not. Okay. So, we will stop here and then we will continue with this example the next time. Thank you.